Just a moment, huh? Vishani, wait for some time.
Yes.
কটা গেছ তুমি পিজ্জা কটা ঠিক আছে
Okay. Vishani, let's start then.
Yes.
So today we are going to start sound. Okay. Mm, in the very beginning, we are going to start. Now, see, let me tell you one thing that as you know that sound is a kind of energy, okay? And how it propagates? It propagates in the form of mechanical wave. Now, what does it mean? Means what is the meaning of mechanical wave? Mechanical wave means the wave which needs mechanical medium to propagate. Suppose if there is a wave which needs mechanical medium to propagate is known as mechanical wave. Okay. Now a question comes that what is the meaning of mechanical medium? What is the meaning of mechanical medium? So let me show you. A mechanical medium is so it is a medium where intermolecular attraction force is present. Intermolecular attraction force is present. That kind of medium is known as mechanical medium. Now, any example of that? Any example? We can call it as air medium, solid medium, and liquid medium. All these mediums are mechanical medium. Now, let me tell you, in all these mediums, no, intermolecular attraction force is present. So that's why all these mediums are known as mechanical medium. And let me tell you, any mechanical wave, it needs a mechanical medium to propagate. Okay. So sound also a mechanical wave. Okay. So sound can propagate through air, through solid, and through liquid. Am I clear? Oishani, am I clear?
Yes, sir.
See, know about audible range. What is audible range? Now, the frequency, what is audible for human ear, okay, no? That is known as audible range, means the sound frequency which is audible for us. Like that range is actually 20 hertz to 20,000 hertz. 20 hertz to 20,000 hertz. So this is audible range. Now, this range is known as audible range. Greater than this range, greater than 20,000, greater than 20,000 is known as, wait, greater than 20,000 is known as ultrasonic. It is known as ultrasonic, and lesser than this is known as infrasonic. Okay, am I clear? Please take a note of
Yes,
this.
sir.
Whatever I'm showing here, no, take a note. Okay.
Yes,
So this is known as ultrasonic and infrasonic. So more than 20,000 is ultrasonic, less than 20 hertz is infrasonic. Okay. Between 20 hertz to 20,000 hertz, it is audible range. Okay. Now see here. Now see, let me tell you the types of means wave, types of waves. See, there are many means in many way we separate the waves. Okay. Now here the mainly whatever we will know, that is longitudinal wave, longitudinal wave and transverse wave. Longitudinal and transverse. Now what is longitudinal and what is transverse? We need to know that. See, longitudinal waves are like, have you seen spring? Have you seen spring?
Yes, sir.
So how the spring oscillates? Suppose if a spring, suppose a suspension spring is oscillating. Okay, in that case, how it oscillates? This is the spring. Means here, what is the medium? Medium is the spring medium. Okay, these are the points. These are in this medium. These are the points. Okay, now how they oscillate? Suppose this, if I take about this point, or if I take about this point, or suppose this point. So how they are oscillating? They are oscillating something like this. They are oscillating something like this. Okay. And how the wave propagate? How the wave propagates? The wave propagates like this, along this direction, from left to right. Now see here, this is the direction of propagation of wave, and this is the direction of oscillation of the particle inside the medium. And can you tell me what is the relation between them? Relation between these two directions? How they are? Are they perpendicular or they parallel?
So
Are they
parallel.
perpendicular? Parallel, right? So in which wave? In which wave the direction of propagation of wave is parallel to the direction direction is parallel to the direction of oscillation of medium. This direction is parallel to the direction of oscillation of particles in the medium, is known as longitudinal wave. Okay, is known as longitudinal. Am I clear? Am I clear?
Yes, sir.
Now I will tell you about transverse wave. Now what happens in case of transverse? If you are putting a stone into pond, suppose you are putting pond. In that case, what happened? You will see waves something like this. isn't it? Now here what is happening? Medium of the particles inside the medium, if you consider, then you will see, let us consider this is one particle, this is one particle, even this is one particle. All these are the particles inside the medium, correct? Now, how they are propagating, how these particles are propagating, they are propagating something like this. They are propagating like this. They are propagating like this. Okay. And how the medium, sorry, how the wave is propagating means how the energy is propagating. The energy is propagating something like this along this direction. It is propagating like this. So in this case, what is the relation means how they are propagating, the direction of propagation of the wave and the direction of oscillation of the particle, how they are perpendicular or parallel?
Some perpendicular.
Perpendicular, right? So in this case, we can say that in which the direction of propagation of wave is perpendicular perpendicular to direction the direction of oscillation of particles in is known as longitudinal, sorry, transverse wave. Transverse wave. Okay, am I clear, students? Am I clear?
Yes.
Now, so this is uh, longitudinal and transverse wave, the definition. Now let me see. Now we will completely come to longitudinal wave, because sound is a kind of longitudinal wave. So sound wave is what kind of wave? It is a longitudinal wave. So the example of longitudinal wave is now here we need to know about the velocity, the frequency, all about all these things. Okay. See, what is all about frequency and all these things, so that we need to know. So to know that, no, if I show it using a longitudinal wave, no, it will be easier for you to understand. Sorry, using a transverse wave, then it will be easier for you to understand. Okay, so that's why I'm showing it using transverse wave. I'm just drawing a wave. Okay, a transverse wave. Okay, this is the transverse wave. Now firstly, what we will know about the transverse wave, that is what first we will know about amplitude. Amplitude. What is amplitude? See, here all these particles, it is oscillating, right? all these particles, it is oscillating like this. Now, this is the mean position. See, the red line is the mean position of all of them. What is mean position? When there is no wave, at that time, all these particles of the medium is actually resting on this line or on this plane. So that is known as mean position. Now, whenever a wave is propagating at that time, these points, these particles, it is oscillating from the mean position. Now, amplitude is the highest displacement of these particles. Now, can you tell me that till from where to where it is displacing? What is its highest displacement? See, from this is from the mean position till here, is it? Or from the mean position till here? So this is the highest displacement from the mean position is known as amplitude. Understood? Question is clear?
Yes, sir.
So we can define in this way that the maximum displacement of the oscillating particle from the mean position is known as amplitude. Okay, understood? You are taking notes now. Whatever I'm saying, you are
Yes,
writing
yes,
that.
yes.
Great. So that is amplitude. We denote amplitude as A. We denote amplitude or capital A. Okay, small a or capital A. And what is the SI unit? What is the SI unit of amplitude? Can you tell me?
A meter.
Yes, absolutely. Because it is displacement or distance covered, so it is meter. Okay, great. So this thing I can say as amplitude A. Next, what we will come, that is after amplitude, we will know about wavelength. Okay, no, we will know about time period. Time period. What is time period? So to know about, before knowing about, we should know something else. What is that? That what is the meaning of a full oscillation? Full oscillation, if I say, what does it mean? Full oscillation means to complete a full path. Okay. See, if I denote it in this way, suppose this is position one, then this is position two, this is position three. When it is going back at this position, that is position four, and again when it is coming here, that is position five. Okay. Now, if the particle is starting from a particular position, and again when it will come over there, again when it will come over there, at that time we will say that one full oscillation completed. Okay. Suppose it has been started from one, it went to three, then again it came to one. It means it is completing its full oscillation. Understood? Now, the time taken to complete this full oscillation is known as what? Is known as what? Okay, is known as time period. Okay, so we can write in this way the time taken to complete the full oscillation by an oscillating particle is known as time. Understood? Clear, Vishani?
Yes, sir.
Then what will be the SI unit of time period? What will be the
Second.
SI unit? Second, right? and how we denote it as T, capital T. Okay, so we got to know what time period is. Now, the next thing is frequency. What is frequency? See, this is oscillating, right? Oscillating. Here on this medium, every point is oscillating. Okay. Now, in 1 second, how many full oscillation a particle is going through? If a particle is going through 10 full oscillation, then its frequency is 10. If a particle is going through 100 oscillation, then its frequency is 100 oscillation per second. If a particle is not performing a full oscillation, maybe zero point 0.5, half oscillation in 1 second, then its frequency will be half. Am I clear? Am I clear? So we can define it in this way, that number of full oscillation a particle is going through is known as frequency. Okay, am I clear? Am I clear, Ushani?
Yes, sir.
Now we would like to know that what is the relation between uh, time period and frequency. Achha, now before that, how we denote frequency? We denote frequency like N or F or nu. Okay, any one of these three we can use to denote frequency. So don't get confused whenever you see N, that also means frequency. F also for frequency. Nu is a Greek letter that also stands for frequency. Okay, and what is the SI unit? What is the SI unit? SI unit is known as Hertz, HERTZ. In short, we write as HZ, or cycle per second. Cycle per second. Okay. Now we will know about relation between time period and frequency. Okay, T and nu. See one thing. What is time period? What we just defined about time period. What we just defined about time period. The time period is what?
Time taken to complete one full oscillation.
Yes, time taken to complete one full oscillation. So if I do simple unitary method, that t, if t is the time period, then in t second one full oscillation is completed, isn't it? So we can write in this way: t second is required to complete one oscillation, right? T second is required to complete one full oscillation. Then in 1 second, how many oscillation will be completed? Can you tell me? If in t second one oscillation, then in 1 second how many oscillation? In 1 second how many oscillation? Simple unitary method. If in t second one oscillation, then in 1 second how many oscillation? Achha, I'm just giving you as an example. Suppose if 10 kg onion costs 100 rupees, then 1 kg onion will cost how much? 1 kg onion will cost how much?
So 10.
10 rupees, right? How you got it? What was the calculation you have done?
So divide.
Exactly. 100 by 10 you did, right? 100 by 10. So here also the same thing you will do.
It's a
T
1 by
second.
tens.
Sorry, what?
1 by t seconds.
Exactly. 1 by t. No, one, not 1 by t second. 1 by t oscillation, right? 1 by t oscillation. Okay. So in t second, if it is one oscillation, then in 1 second it will be 1 by t oscillation. See the definition that in 1 second, how many full oscillation is completed? That is known as frequency. So can't we say that frequency is equal to 1 by t? Understood or not? So this is the relation between frequency and time period. That frequency is the uh, reciprocal of time period. Okay, understood, students?
Yes.
Oceani? Okay.
Yes.
Now the next what we will wavelength. Wave length. What is wavelength? See, uh, wavelength. What is from this name? What you can name? What you understand from the name? What you are getting from the name?
The length of the wave.
Length of the wave. A bit. I'm just editing over here that length of a complete wave. Okay, length of a full wave. Length of a complete wave. That is known as wavelength. Okay. Now see how we will know that how a complete wave is forming. See, if you see this, okay, see these points, this point and this point is in same position, or this point or this point is in same position. Do you know what is the name of these points? The point which is at the highest and the point which is in the lowest displacement. The highest displacement is known as the highest displacement is known as crest, and the lowest are known as trough. Highest is known as crest and the lowest is known as trough. Okay. So the length between two consecutive crest or two consecutive trough is known as wavelength. Okay. So length between two consecutive crest means this is a crest, this is a crest. Sorry, this is a trough, this is a trough, this is also a trough, this is a crest, this is a crest, this is also a crest. Okay, so the length between two consecutive crest is known as wavelength. The length between two consecutive trough also is known as wavelength. Okay, so this is known as wavelength. Okay, we can define in this way. We are writing the length between two consecutive crest or trough is known as wavelength. Known as wavelength. Understood? Am I clear?
Yes.
Now, see here is known as wavelength. Now, how we denote wavelength? We denote wavelength as lambda. Lambda is also a Greek letter. We write it like ulta y. Okay, inverted y. So this is known as lambda. Okay. Now see here. What is the SI unit? What will be the SI unit? What will be the SI
Meter.
unit? Yes, meter again. Why? Because this is the length.
Length.
So that also we got. Hello, fine. Now we will get the relation between velocity, time period, and frequency. Okay, and also lambda. I should not say between, I should say among. So relation among V, D, nu and lambda. Okay. So here I will draw the diagram once again because it's already far apart. Again and again I need to go. That's why I'm doing it like this. See, this length is known as wave. Okay. And let me tell you that means velocity of the wave is what? Means in which velocity the wave is propagating. Okay. And let me tell you, to propagate a distance equal to the wavelength, a wave takes t amount of time, means time period amount of time. Okay. So in this case, what we can say that velocity is v, distance covered by the wave is what? Lambda. Time taken to cover that much of distance is time period, capital T. Then can't we use d is equal to distance is equal to velocity into time? So in that place, if I put the value of distance which is lambda, v, and the value of time which is t, so lambda is equal to vt. This is a formula. This is a relation. This is the relation between lambda, velocity, and time period. So this is one relation. Now also we know that t is equal to 1 by n or 1 by nu, isn't it? 1 by frequency. T is equal to 1 by frequency. Therefore, in place of t, if I put 1 by nu, 1 by nu, then v is equal to also can be written as nu lambda or f lambda, means velocity is equal to frequency into wavelength. So these are the two formulas. Okay, no, we get. Am I clear? Am I clear?
Yes.
Okay. So just note it down. Then we are shifting to the next topic. Done. You have done copying.
Yes.
Now, one more thing I would like to see, like in case of transverse wave, I have shown all the things. In case of longitudinal wave, also you need to see all these things. Okay, no? See, if this is the spring, see at this point of time, all these points are equidistant. It means at this point, there is no force applied. No force is being applied. But whenever you will apply some force and the wave will start propagating through the spring, at that time, how it will propagate? Somewhere it will become like this, somewhere it will become like this, again like this, again like this. Okay, means what happened? Somewhere they became highly dense and somewhere they rarefied. Okay, see, this is known as compression and rarefaction. Okay, what we call it? We call this as compression and this as rarefaction. Now, like you have seen in case of transverse wave that the distance between two consecutive crest or trough is lambda. Similarly, here also the distance between two consecutive compression. See, this is also compression. This is also compression. This is rarefaction, and this one is rarefaction. So the distance between two consecutive compression is lambda. Similarly, distance between two consecutive rarefaction also is lambda. Understood or not? Understood or not? Hello.
Yes.
Great. Now, so that is in this way, longitudinal wave propagation. Now, I would like to Specifically, I will show you that how sound propagates. The way sound propagates. The way sound propagates. Which way sound propagates? See, suppose I'm showing the propagation of sound through air. Okay, the way sound propagates through in air medium. How it propagates? See, if I consider the air as the air medium as layers. Okay, no? See, air medium in the form of layers. These are the layers. See what I'm drawing? The layers, all these layers I'm drawing as equidistant. All these layers are equidistant. All these layers are equidistant layers. Means at this moment, no sound is propagating. No disturbance is being created. Once we started creating the disturbance, what will happen? These layers, somewhere they will come very close. Somewhere they will come very close, like this. And somewhere they will go away from each other. Somewhere again they will come close, and somewhere they will go away from each other. Okay, so it means somewhere the density will increase and somewhere the density will decrease. This is known as compression. This is known as compression, and this is known as rarefaction. Understood? In this way, sound propagates in air from one place to other place by changing the density, by creating compression and rarefaction at different places, and in this way it keep on moving from one place to another place. Understood? Understood?
Yes, sir.
And let me tell you one thing. That's why in vacuum, suppose where no, see, if sound is propagating, it means it is propagating. Just a moment. Just a moment. Hello, Ishani, can you hear me? Hello? Hello, Ishani, can you hear me?
Yes, sir.
Hello? Yeah, yeah. Okay, chalo, let's start. Huh? Sorry for the interruption. See, so in this way, sound actually propagates. Now, what I was telling you that why sound can't propagate in a vacuum? Because see, sound, the way of propagating of sound is by making, by compressing and rarefying the medium. Now, if the sound don't get any particle to compress or to rarefy, then how it will propagate? That's why in sound, in vacuum, sound don't propagate. Okay, no? Like suppose in outside of our atmosphere, of Earth's atmosphere, whatever is happening, that sound won't come to us. Why? Because outside the atmosphere there is complete vacuum. That's why sound won't be able to propagate through that vacuum. Understood? Am I clear?
Yes, sir.
Great. Now, coming for the next. So till here you have written all the things, no?
Yes,
Uh,
sir.
Great. See,